Hi all, this is an interview with Clara Meister, who is the first author of the paper Typical Decoding for Natural Language Generation. This paper, I believe, is really important because it presents a new sampling method that makes language models output much more human-like texts. I've already made a review about the paper. If you haven't seen that yet, check it out. Clara has seen it and we're able to dive directly into the matter. This interview was very cool. I learned a lot. As always, if you like, leave a like. Tell me what you think in the comments, and I'll see you around. Bye-bye. Hey there, today's sponsor is the course on Introduction to Graph Neural Networks. This is a course by my friend Zach Jost, who is an expert in graph neural networks. He's packed all his knowledge into one course that will educate you on both the theoretical and hands-on practical aspect on graph neural networks. Graph neural networks are really important. They're definitely one of the most interesting areas in deep learning right now. They've also powered a lot of recent advances in scientific breakthroughs, such as AlphaFold protein structure predictions or better traffic predictions. If you use my link, you'll get a 15% discount on the course. Enrollment is open right now and lasts until April 1st or until spaces run out. All right, let's get into the video now. See ya. Hello, everyone. Today I'm here with Clara Meister, who is the first author of the paper Typical Decoding for Natural Language Generation. Clara, welcome very much to the channel.
Thank you, and thank you for having me.
This was a really neat paper. I have to say I have just finished my last interview, not just now, but I finished my last interview about a system called Blip, and what they said is essentially they have a system that generates captions for images in an automated fashion. And then they have a filter that kind of weeds out the crappy captions. And they use that as a means of generating more high quality data. And they and many others before them have found that how you sample from a model, like from the language model they've trained, matters a lot. Specifically, they told me that nucleus sampling in their case was really a defining factor in getting more of a diverse sample set. And they particularly compared it to greedy sampling and to beam search, which they found super underwhelming. And I've come across a lot of systems in recent times, for example, AlphaCode as well. I don't know if you know how exactly AlphaCode does what it does. I don't either, but from the paper I could gather that they sample a lot of potential solutions and then they reduce those down by filtering and clustering. And again, there they rely heavily on being able to sample diversely and to sample, many different things. And I've for a while now thought, maybe our sampling objectives are wrong for certain applications, namely for the applications where we actually are interested in more of a diverse output rather than the most likely output. And along came your paper, which essentially exactly plays into this and suggests a new method. So I was super happy to see this. I think it really hits sort of a nerve of the time. If you would pitch it, like the elevator pitch for the paper, what would you say about it?
I would say that, specifically for language generation, I think with these large models that we've been training, that when we're generating language from them, we kind of need to take into account like what we really want from the model, what our objective is. And also what we just normally do when we're speaking, when we're writing, like how we use language. Trying to think about having like this, what these models are is essentially like probability distributions over strings, right? And that's kind of a strange concept, right? It's like, that's not probably how we imagine language in our heads. But there is some like evidence in psycholinguistics that that's kind of actually a pretty good metaphor for how language is represented in our head. And then, how we then go from that to generating language, and what the characteristics of the language that we typically generate are. I think, we really want to take that into account when we're trying to generate language from these models. If you ask me to if you just ask me to say something randomly, right? I mean, it's like, what am I going to say? I'm probably going to say like, I don't know. I mean, it's like, I don't really have like these really common phrases. But if we want something more interesting, like if you want me to say something more interesting, then I'm going to not just pull like the most likely sentence out of thin air. I'm going to try to convey information in what I'm saying. And, I think that these models have sort of learned how to do that implicitly. And we can ask them then to try and do this in a similar manner to how humans do.
So you pretty quickly get to this notion of typicality, which is a notion from information theory. You connect it to various disciplines in psycholinguistics. But a typical message, as far as I can understand it, is, well, as the name says, one that you would expect to see from sort of a communication apparatus. Mm-hmm. But it is, do I understand this correctly, is one that you expect to see if you assume that the communicators want to transmit the optimal amount of information.
Yeah, and
is this the core assumption behind sort of the how we think about communication between humans?
Yeah, I mean, so one important thing is like typicality in the context of communication channels is really only defined in the context of a message here, some sort of message that you're conditioning on and trying to convey. So, and here, I mean, especially when you're like sampling from a language model without having like this implicit message that you're conditioning on, in the background, I think it's kind of hard to really, quantify what a typical message in natural language should be. And I think we're very careful to say that there is this nice intuitive link between typicality and how humans use language and what type of strings we might expect when using natural language. But there's a lot of aspects of human language that don't really fall into the paradigm that you can really apply typicality to.
And yet, you inspire, let's say, by this notion of typicality. You're inspired by. So you define the notion of a typical message, and that is sort of the average information content you would see. I made a bit of a characterization in my video. By the way, we have to inform the viewers that I used the old archive version, and you just updated it. And you corrected essentially all the little criticisms I had about notation and things like this, just to get the lore right. It wasn't me that caused it. You did it ahead, and then I.
Props
I used
to you
the old
for
version.
picking them out. Yeah, my advisor always says that like every single paper out there pretty much has like math errors in it.
Oh yeah.
And
don't worry.
It takes a critical eye to find them. It does. It's super easy to just glance over them, not realize it.
Well, I think it was actually straightforward. The paper is really easily readable. So when we think about how humans communicate, and let's assume for a moment what you say, that in your hypothesis here, any given word should have an information content close to the expected information content, i.e. the conditional entropy given prior context. In other words, we expect this difference to be small in human-like text. And you also say that the human goal over here is to transmit information effectively while also minimizing the risk of miscommunication. I made a bit of an example right here, as if I explain math, or if I explain the chain rule to someone who does and does not understand math. Is this an appropriate example? Is this an appropriate metaphor for what you're going for? Or is this totally off?
No, I mean, I think in a way that's right. I mean, I think that's actually perhaps even more related to what we describe later on, which is like the rational speech act, which is, how we also are taking into account the listener, right? When we're forming our messages. So, I mean, that's definitely a component that's taken into account. So we'll modulate the amount of information that we are conveying to basically like, to account for what the other person might know. And I think that you can kind of model that in different ways. You can say that in your case, like, I think how you put it, I think is a totally valid way to see it. In that case, we can say that the information content for the speaker is going to be much higher than for someone else. So, I think that's a good comparison.
So this notion of the expected information content is pretty important here. And we say, okay, if I'm at a certain, let's say I've uttered half a sentence, and then I look at the distribution of the next word. And that distribution is just the distribution of the language itself, if I understand this correctly. So I have my training corpus, which supposedly is all of human language. I analyze it in my head. I determine what's the conditional probability for the next word in the training corpus. And then your claim is that what I do is I don't actually sample from that distribution. I'm going to adjust inside of my head the distribution that I sample from to words that closely match the expected information content. My question is, why do I do that? Like, I see the problem with always picking the highest likely word, right? If I have a broad distribution like this, I don't want to do that. I don't want to just pick the most likely one. However, why can't I just sample from this distribution? It seems like enough times I would actually, pick some other words that is also completely fine.
Yeah, so first of all, I think one thing is when we're forming language, we arguably aren't like sampling from this distribution, right? We kind of know, maybe to some extent we're sampling what word we're going to say next. But I think the important thing to internalize is that we have a message that we want to convey, right? Every time that we're using language. And the way that we choose to do that is, at a specific information rate. Because we want to communicate efficiently, but we also want to make sure that our message gets across without having to repeat ourselves or confuse someone or making them spend an inordinate amount of time processing what we're saying. And so because of that, we're not going to choose super low information words all the time because that's just kind of inefficient. I can say all these filler words, right, and still get across a message, but adding it's like that, that person that takes forever to explain something just goes about it in a super slow and redundant way.
Hey, don't make fun of my videos.
What? I wasn't. What are you talking about? So I think that's something to think about. And then, sorry, the second part of your question, I've already forgotten.
I think what I've understood is that if we look at just the distribution of the next word, that is in all of language, that is across humanity, everyone who's uttered ever that first half of the sentence, this is the distribution of next word. However, when I consider that I actually have a message to convey, that distribution changes, right? Is that about the characterization of why? My question would be, why don't I just sample from this distribution right here, given that if, many words are possible, it will actually result in kind of a diverse sampling?
Yeah, I think that first of all, I actually do think that in the case of a perfect language model, that you could actually sample from this distribution and be fine. I think that there are some artifacts that are a bit strange, especially in models that aren't trained as well, with this long tail distribution that that tail isn't necessarily learned very well, what those actual probabilities are, and so you end up with just oddities. But beyond that, I do think that we're not. We are trying to modulate when we speak, the amount of information that we have per word, right? To keep it even. And this is not, this is something that is perhaps not very obvious, but it is something that's well studied in psycholinguistics, how we convey a message. And the coding that we will use within natural language. And so, like, yeah, we take this into consideration when choosing the next word. Not to be too redundant or to be too surprising.
Yeah, and again to transmit what we actually want to transmit, right? Because I have something that I want to say, and that means I can't just blindly sample from the distribution. I would never actually transmit what I wanted to say. Would it be possible that, let's say, if I could hypothetically determine, what kind of, let's say I have a message I want to transmit, could I somehow define the information content of the next word given the message I want to transmit, and maybe also given the sentence, so far t smaller than or smaller than t?
Well, that's that's actually usually what we're doing in a task like abstractive summarization, which we see is something that we experiment with. We are conditioning on that message essentially. Yep. That message being the article. Right. And so it is like we are taking that into account when we're trying to build our next word. And it is still like this distribution should reflect the fact that there is a message that we want to convey. And, given that message, it sort of reflects that, maybe this word that without that knowledge would have been very surprising, but like with that knowledge, with knowing that like we want to transmit this message, actually that word is like what we would expect.
Yeah. Okay. My question, what I'm trying to get at is, if I train my language model for abstractive summarization, right? The conditioning of the message is maybe already not maybe in here if I use a decoder only model, but like, my question is still, why is this distribution here not enough? Like, why do I need to cut out the most likely things, even though, sometimes I actually want to say them?
So, I think it's just to be more human-like. That's the most I can say is...
it's fine, right? So you come up with, and we're gonna go back to these plots because I find them super interesting as well. You define this typical sampling strategy where you say, okay, we have this thing here, which is the expected information content of the next word, and then we're just trying to, as closely as possible, match that. So we're just going to select a subset of all the words that we could pick, which closely match that expected information content according to your hypothesis. And then we're going to sample according to the new distribution that only consists of the subset of these words. So in the video, I think I raised a point which is maybe more of I don't know if it's circular logic or a philosophical point, but all our training data, presumably of these language models, comes from humans, using language, transmitting information. Therefore, right, shouldn't, like, if I now train my language model and I use your method to sample things, and you claim it's a human-like way of sampling things, shouldn't that A, result in the same distribution, and B, shouldn't it sort of, the expected information content, if I measure before and after, like if I measure it in the training corpus and then if I measure it as an output of my model, shouldn't that be the same? Because presumably the training corpus is already generated from humans.
I think so yes, I think that makes sense if I'm understanding correctly. And I also think we're kind of seeing that, like in the earlier plots, we're actually seeing that if there is like an average amount of information, right? According to the model, there's an average amount of information that each word will contain. And human text seems to be coming from quite close to what the model has learned that average information rate to be.
And did you investigate the outputs of your model and sort of redid those plots on the output of your model and observe the same pattern?
Yeah. So That's something we did as well. We looked at basically a few different decoding schemes and saw what these distributions looked like for the outputs of those decoding schemes. And I mean, things like, it's a nucleus sampling with like very popular values of P looked similar, and so did the ones from typical sampling. I think honestly they do look. Visually, they look pretty similar, which is nice. It's also nice to see that sort of these vetted decoding processes that have stood the test of time are also actually mimicking these distributions. I think that if we wanted to be robust about it, we'd probably want to, come up with some sort of quantification for how different these distributions are, and use that perhaps to see if that correlates with how well these decoding methods perform in terms of things like human evaluations.
So can you tell us the story behind these plots a little bit more? Because you define epsilon in terms of an absolute value, yet here I see values that are less than 0 to both sides. So I didn't know which one is which.
Yeah,
what's
I
epsilon here?
For that. I tried to make it clear in the caption of the text, but I don't think I did.
I mean, if I guessed correctly, it's the conditional, it's the expectation minus the actual information.
No, so it's actual information minus.
See, I would have gotten it wrong.
Oh wait, no, I think you're right. No. Oof.
But
okay, so
maybe you can tell us what does it, because these are kind of, so it's more, if I see this correctly, more sort of mass on the left side of these, close to this boundary, which is really interesting. And then there's a long tail on the right-hand side. Yeah. What does that tell us about human language?
I mean, that's like a very deep question, and I'm not entirely sure about what the shape of this distribution means. And I think it's very interesting that this is the shape of the distribution. And actually we used a few models here, and all of them kind of did look like this, where you had like this peak and then sort of a long tail. And I think that's like an investigation in its own right about how humans use language. By the way, it is information content minus entropy. So remember, it's like low information content, high probability, right? So actually human language tends to be to the, like on the higher probability side of conditional entropy.
So this thing right here.
Yeah.
So if we're way out on the right, it means that we actually transmit a lot of information, actually more than would be expected.
Yeah.
So there is a long tail of very high information words, let's say. Do you think, so because you, in one thing that I skipped over that in the video review, but you make this point of humans, what they probably do is they want to, everywhere in the message, they want to have kind of a constant information rate. So every word should approximately transmit this expected information. So as you go through the sentence, do you think this could be violated a little bit? Because humans, most of them do tend to have like a short-term memory of 3 to 4 words or so that they can keep ready in the sentence. Maybe I can transmit this super high information word, and then before my receiver gets super confused, I can follow that up with like 2 or 3 clarifications, which would be then maybe here in the lower information content, but they would be more.
Yeah, I mean, so like I think it's hard to always avoid moments of high information. I mean, for example, if you think about this very literally in terms of like what those words could be, they could be like someone's name, right? Mm-hmm. And that's kind of like you're introducing someone. That's always kind of going to be like a high information moment, right? You have to remember. I mean, if we always forget people's names, obviously there must be a lot of information in those names. It's a very off the cuff explanation, but. So I think it is hard to just 100% of the time avoid those instances. But I mean, this is talking about sort of on average what we're doing when we're constructing language. And I mean, so I guess I couldn't say whether in those moments we try to perhaps on either side balance out, like with lower information words, this high information word, because I mean, you know, maybe we do in order to give the listener some time to internalize this information. But there are also, especially with speaking, which is a different domain than writing, right? There are other ways that we can modulate high information words, right? So we can elongate our speech to basically spread out information over time, right? And so it's not like here we're just evaluating text. So, you know, I think especially in text, we're going to see these longer tails because you can't sort of distribute information over too many words in certain cases, like in the case of introducing a name. I think that's...
And also it has to be said that, you know, you can, if you go to the left, you get into the super low information words, and there is only that many of them, right? As soon as I'm at the and right, there aren't that many. But however, there is in fact a long tail just in the language of super high information words that are quite unlikely. So maybe that plays a role into it as well. About these plots, you draw two different conclusions right here, which the first one is the peaked nature reveals that humans indeed tend to form language with per word information content quite close to their expected information content. So this is kind of, you know, here is data that shows our hypothesis is correct. And the second one is the centering of these distributions around a value close to zero reveals that our probabilistic language generators are learning what this rate is, and my point was a bit, when in order to make point 1, you need point 2 as an assumption, right? You need to claim, well, I can only say this because I assume our language models are modeling the probabilities of language well enough. Otherwise, I could not conclude point 1. Likewise, you couldn't conclude point 2 without having point 1 as an assumption. Am I overlooking something here?
Well, so, I mean, I think the point here that we wanted to get across was really that, you know, two things should be looked at in these graphs, which is the centering of the graph and also the shape of the graph.
Yeah.
And I mean, so I think there is an assumption that kind of has to be made here. I don't think it's quite as severe as what you've mentioned, but I mean, it is sort of that this information rate is kind of a ground truth of sorts. But I mean, you know, you could, for example, shift that entropy rate. You could shift the entire distribution and still, you could shift H and all the P's and, you know, all of those numbers and still technically get the same distribution. So that, I agree with. But like, I mean, I think like looking at the peakiness of it, clearly we're seeing that, you know, humans are generating language around a certain that
something, right?
Content.
Like,
yeah.
Like what if it were centered around 2 instead of 0, right? It would be as peaky.
Well, yeah, I mean, as peaky, then like we'd probably be, that probably show that humans communicate at like a very low information rate, right? So, but no, I mean, it's around, like, it does seem to be close to this expected information rate. And I think one other, like, the part 2 is really trying to show that, like, there's this, we would expect that if our model understands that, you know, humans are speaking at around an average information rate, that this distribution would be centered around, like, on average, it would be predicting that information rate for a given word, or like that information content, that probability for a given word. And it does seem to be doing this.
Cool. Yeah, this is just a bit of a nitpick for me. I'm totally on board with. I mean, it's pretty clear the language models do model these probabilities relatively correctly, especially the ones with the higher probabilities. And I'm fairly convinced by these plots.
I think
what
you
you're
bring
doing
up
is
a
something
really
sensible.
important point, and I'd spent a long time thinking about whether or not it was too circular, whether you could have one without the other, really. And I think at some point I came up with some examples, like some counterfactual examples where actually you could have one without the other, and of course now I can't remember what they are, but.
Yeah, it's I think people understand what you're saying there.
And there's definitely like a degree of freedom there, right? There's definitely something that could change, that you could get those same results. And I think like that thing that could change would be whether the information rate learned by the model is like the quote human information rate, the actual human information rate. And I'm actually not entirely sure that's important. It just has to get it right, like relative to what it's predicting the probabilities for words, right?
Do you want to tell us a little bit about the experimental results? Because I have not gone into these at all during the paper review. Things that you would like to highlight or anything like that?
Yeah. So, as Yannick mentioned, there's a new version on arXiv where we also present a few different values for nucleus and top K, as in like the same number of values.
Oh yeah, the hyperparameters. Sorry about that.
No, I think it's very reasonable. I mean, the thing is, there were only so many human evaluations we could afford, and we thought we should probably test out more values of our own method since no one has done this before. But a lot of people have looked at nucleus and top K sampling. But then once it seemed like, okay, this is research worth doing, we were able to get a little more money and launch a larger human evaluation. So those results are now in the paper. I think one thing that was really interesting for us was actually just the variety of values of tau that worked well. Mm-hmm. Basically, most values of tau worked well. Okay. There wasn't a huge difference between all of them, which we thought was really cool. Because in comparison to nucleus and top K sampling, those methods were really dependent on N and K. And I think there was a little if you just look at the output of these models, if you have a large tau, then maybe qualitatively you could say that the text is a little more normal, a little more standard, and then maybe a little more diverse for low values of tau. But basically, it was just interesting to see that for these two tasks, at least, that variety, it wasn't, you didn't really need to tune tau that much. Just kind of worked.
It's important, right? Because that's one of the issues with these things, is that if I have to tune the thing to every new task I do, I'm a lot less certain in kind of the generalization of this, even within the same domain. But if it's interesting to hear, and if it's really a kind of a handle on the craziness that I get out of these models, that could actually be even a cool property, right? Mm-hmm. If you say, actually most values work, but it is, it changes just the style, I think that is a useful hyperparameter rather than a nuisance, like in nucleus sampling. If I don't get it right, it's going to be crap.
Mm-hmm. Yeah, well, I would like to think that that's the case. I'm slightly biased here.
Is there any? You run various automated tests in abstractive summarization and story generation. Most of the time, the typical sampling is on top of the pack. Sometimes not, especially here in the story generation on some of these automated evaluations. Is that kind of an interplay between the evaluation, how the evaluation is done, and the methods, or is that a property of the task itself? What can you tell us about this?
So I think a lot of these metrics can only tell us so much. The text that we end up generating, how it performs in terms of these metrics. I think you'll see, for example, in human text, you'll get reasonably different values. Like you can get reasonably different values for things like repetitions, and if within reason, and the text be, equally as good, at least qualitatively. So, like, I think the important, I don't know if it's important is the correct word, but one of the critical things for us was like looking at whether we could avoid this really degenerate behavior with models, because I think that's something that's like one of the bigger problems in language generation, is just like this tendency for these methods to fall into repetitive loops. And I mean, we basically just like we didn't really see any of that in using our method. And so I think that was an important takeaway. So yeah, I mean, always kind of performing well in terms of this, in these metrics that show how repetitive or redundant text is. I think it is what we would expect, right? We're saying that like if text is, we want text to be about as redundant as human text is, because that's like one metric you can use to quantify information content, right? So it was good to see that like at least it's a necessary, not sufficient criteria, but it was good to see that it was met.
Yeah, I was just looking at perplexity, and yours is in bold, and I was like, wait a minute, lower perplexity is better usually. But then I realized what you have to do here is obviously match the perplexity of the reference text as closely as possible. So the goal is to be as close as possible to that number, which is really astonishing to see, because in machine translation people are fighting for 0.1 perplexity or so for the new state of the art, and here it's a difference of it's quite a magnitude of difference between these methods, which is cool to see, and I think shows quite well that in something like story generation, these models might really just overfit is the wrong word, but overproduce not as creative outputs, or maybe even degenerate ones, as you say.
I mean, I think actually in the context of machine translation, and this is something that an experiment that I want to personally perform, is look at what the like average perplexity of the reference text is, right? I mean, so, and the generations, right? I mean, so the one thing about machine translation is like typically we're evaluating on things like BLEU, right? Not perplexity so much. So we're evaluating on the generations themselves rather than the evaluation of the reference text, like what the perplexities are. But I mean, it would be interesting to see what, good generated text, what the perplexity of good generated text is compared to human-like text. And I think in that case, they would actually probably both be quite small. At least that's my intuition. Of course, one artifact that I think would kind of get in the way of these experiments is the fact that machine translation often uses label smoothing, right? And label smoothing is basically like a form of entropy regularization. So it makes these distributions higher entropy, even
if they shouldn't be.
Yeah, and that actually, I mean, basically. You can read other papers about this that'll explain it, but it does interact with beam search. Like it's like the match of beam search plus label smoothing tends to work quite well. But I think if you were to really perform these types of experiments to understand what the types of perplexities for for translations or good translations would be, I think you need to do it with a model that hasn't had this sort of artificial inflation in entropy.
Do you think our training objectives are the correct ones? Let's think of something like story generation, because what I'm hearing now is that label smoothing but plus beam search works, but it's more like a hack to get around the weaknesses of beam search without label smoothing. Do you and that is something I can maybe, get behind. Do you think we have the correct training objectives if our goal is really to create a diverse and interesting set of outputs? Do you think it's a good strategy to train, let's say, maximum likelihood and then sample using something like typical sampling, or should we also change our training strategy?
So I personally think that maximum likelihood is a pretty robust objective. I mean, in terms of like the information theory perspective, I mean, when you are maximizing likelihood, right, you're also minimizing KL divergence. So you are basically looking for the model that assigns the same information contents to strings as the empirical distribution, right? So they're just equivalent. And so I think if you take that into account, basically if you take into account exactly what you're doing with your objective, and then from that, go on to, okay, well, given this distribution, right, how would we as humans go about generating from this distribution? Or, if like you're generating an image, like how would nature go about like generating from this distribution? I think, that it's really important I don't think there's a correct way necessarily to go about training and decoding, but I think we really need to take into account more their interaction and understand like what is going on within that interaction.
Yeah, I mean, I'm all on board because it also means that we can reuse the same model for multiple, let's say, tasks if we swap out our decoding strategy. Can you tell us a little bit about these plots and what we see here?
Yeah, so this is more just showing the repetition values. So kind of what I was talking about earlier. So high repetition values would indicate that we're getting into kind of like degenerate loops, like repetitive loops. So where the model outputs the same thing over and over again. And we really see this in story generation for low values of K and N, where, yeah, exactly there. So, these are like repetition values of like 0.8. So it's just like really just spitting out the same exact thing over and over again. It's like, I think that looking at this type of behavior in terms of information theory, it actually really makes it make sense why this is happening, right? If we're saying that we're always going to output the most likely word, like those are also the words that just have like no information content, right?
And also, like if I come to you and I say, look, here is a sequence of words. It goes apple, banana, peach. Apple, banana, peach. Apple, right. Banana, and then to ask you like, what's next? I mean, it's quite likely that peach is the next thing, and that explains very well why if you keep repeating, you're sort of reinforcing even that repetition, because as you keep repeating, the next repetition becomes more likely. Yet the transmission of information is almost zero. Yeah.
But I think one thing that would actually be really interesting, one set of experiments that we have yet to run, is to see, if before you get into these repetitions, like if you start with something and then if you start with one phrase and then go into typical sampling, right? Can you prevent some of these repetitive loops because you've now come in with the objective that you want to transmit like more information. You don't want to transmit like a small amount of information, which is achieved by like doing by giving high probability low information words, right? So kind of seeing if typical sampling can almost help us break out of repetitive loops.
Although by your own what you wrote, if you are, let's say, in such a loop, or at the beginning of such a loop, the distribution would be extremely peaked, right? And at that point, typical sampling would also go for the high probability words, or is that?
And honestly, like I think it should, right? Like at that point, but this is kind of why it's like before you get into the repetitions, right? So like at that point, where something like nucleus sampling might decide like the lowest information choice is just to repeat what's already been said. If we can prevent those types of behaviors.
Just some small technicalities, where I want to ask you if you think that it's appropriate. Do you think the absolute difference is an appropriate measure, or why did you decide on that? That's the first thing. Second thing is, do you think this cutoff, this hard, I'm going to take this many words and then I'm going to exclude the rest, and then I'm actually going to sample from that bunch of words as if it were like the original distribute, like with their original logits. So just the technical implementation of the idea. What could be, like, what are arbitrary choices? What are things that you did for a reason, and how could they be better?
No, I think that's like a great question. Why absolute value versus squared distance, and why the hard cutoff? To be honest, I think that this was the original instantiation of the idea, was just choosing words from like near the information content, near the expected information content, and I think in order to really introduce this concept into the literature, it helped. At least what I thought was that it would help to have something that was akin to what most people are familiar with, which is nucleus and top K sampling, right? And so for better or worse, this method was kind of like, okay, here's something that's very parallel, that'll be easy to understand. It's also just truncating the distribution, also like looking at the specific portion of the distribution, and that's where we'll sample from. Now, whether it's better to use the squared distance, we ran some additional experiments later on, like after releasing this draft, looking at things like the squared distance and trying to come up with a soft distribution. And yeah, they worked about the same, sometimes a little bit. Honestly, I think I think there's just a lot of research to be done here. I think there's a huge body of research that can be done in sort of figuring out exactly what our objective should be. Perhaps learning this objective, like learning what the correct formula right here should be. And that's to come in the future. So I can't say that square distance isn't better. Very well could be.
All right. Is there anything else you want to get rid of? How can people get started with this? Is there code somewhere? There is code, right? I've seen that.
Yeah, there's actually code in Hugging Face already.
Nice.
So if you have, I don't know if they've released a version since it entered the library. It's been in there for about a month now. So I think if you have the Transformers, the Hugging Face Transformers library installed from source, if you have pulled it in the last month, it'll be in there. And when you generate, if you just add in the argument typical P equals something, then you'll have typical sampling. Nice. And I really encourage people to play around with it. You're going to expect me to say this, but I've actually just been really impressed by the outputs of typical sampling. Just that they have been pretty high quality from my perspective, and interesting. Yeah.
Cool. Clara, thank you very much for coming here. And
thank you. Thanks for the great conversation.
It was a pleasure.
Maybe you'll see another update on archive with some of the things you've pointed out. Clean up some of my arguments.
that would be excellent lore for the channel.
Yeah.
Cool. Thank you.
All right. Thank you.